Welcome to ToKCast and to episode 200, plus or minus one, depending upon the platform you happen to consume ToKCast on. I began this podcast purely to help me clarify in my own mind the ideas of David Deutsch, which then became David Deutsch and Karl Popper, and then it became David Deutsch, Karl Popper, and related thinkers. One of those related thinkers is my guest today. I have a guest, Chiara Marletto. It is rare indeed for me to have guests at all on ToKCast. It's just never been that kind of a podcast. It's more a monologue kind of a podcast. Not that I'm necessarily a monologue kind of a person, or am I? Of course, like almost every human being, I am primarily talking as part of a conversation with lots of other people. Nothing remarkable there. But these days, many of those conversations are indeed actually recorded. And the place I prefer most for this is AirChat, which is a new app founded by Naval Ravikant and Brian Norgard. When I was a kid, I used to get involved in these strange conversations. I'm sure you had one as well. What would you prefer to lose if you were forced to choose, your sight or your hearing? I think I used to always say, take my hearing, I can deal without that, I'll keep my sight, thanks very much. But these days, I'm not quite so sure. I think I like to listen and talk. What Naval and Brian are building at AirChat is a place not merely to have conversations, but also it's a new way of creating podcasts. And that, of course, is centre of the bullseye for my interest these days. I've got lots of fancy equipment here and try to make myself sound a lot better than I do in real life. But it is a job of work, as the British might say, to actually produce something like an episode of ToKCast. AirChat really streamlines things and is a marvellous supplement to this podcast, ToKCast, for me. It's a genuine way of turning this one-way channel of information into an actual two-way dialogue. It's talkback podcasting, and I absolutely love it. So come and talk to me at AirChat. Just search the App Store, or whether you're an Apple person or an Android person, just wherever you get your apps from, and you can find AirChat. It's better than Twitter Spaces or X Spaces, whatever they call it these days. It's better than voice messages left using Facebook Messenger or WhatsApp or whatever else you might have tried. AirChat has all the bells and whistles involving studio level production, also AI and automatic translation, export facilities. It's got all of that stuff, but it's still simple to use. It sounds like an advertisement I'm doing here, doesn't it? Well, it's not, believe me. It's just me singing the praises of something that not many people hitherto know about. It just happens to be something that I use near every single day. I mean, I'd sing the praises of my iPhone here, but you know, everyone knows about iPhones and Apple products, and they need no special promotion by me. But for now, AirChat does remain a hidden gem on the internet. ToKCast isn't going anywhere at all, but as part of a celebration for this episode 200 of my podcast, I want to let fans know that if you want to talk to me in person, I'm super responsive on AirChat. And, well, never mind me, you can actually talk to Naval yourself and a whole bunch of other people with really diverse interests. And if you've ever thought about getting into podcasting yourself, but you just think it's too difficult, well, AirChat could be a low-resistance way for you to do that. But let's get to today's episode. One of those rare ones in which I'm actually talking to someone else. I completed the Beginning of Infinity chapter exploration some years ago now, and I spoke to David Deutsch for episode 100. And at that time, I'd already commenced my explorations of his other book, The Fabric of Reality. And I began branching out, discussing some of Popper's work and comparing it to other thinkers, people like Sam Harris or Ayn Rand or Max Tegmark, lots of other people and their ideas. And Chiara Marletto published her first book around about this time that I began talking about the fabric of reality. And that book, The Science of Can and Can't, was the first popular, accessible to the layperson account of constructor theory. A new theory of science at the foundations of physics. I think popular science, for want of another term for books like this, has an absolutely crucial role to play in culture, in transmitting our best ideas. I've said over and again that I could and indeed did do university physics even to a master's level, but none of it much helped me truly understand what was actually going on in quantum theory, like the work of David Deutsch did. His book, The Fabric of Reality, Chapter 2, Shadows it's called, did more to help me understand quantum physics than multiple years sitting in lectures, tutorials and labs did at the university level, with fancy titles like Quantum Physics and Relativity 101 or Higher Quantum Physics 201. Any of that official type formalized stuff just didn't do it for me in the way that Shadows from this book happened to do. So when I first discovered that David Deutsch was working on a new theory of physics, and I read his technical papers on constructor theory, I began to read more widely into what this constructor theory stuff was, what von Neumann himself had said on the topic of a universal constructor, and then what prior thinkers had ever written about in terms of counterfactuals. I'd already done some philosophical work of my own on that at university. All that technical stuff can quite easily blow by you if you're not really engaged from the get-go on what the problems even are that this new theory is trying to solve. Well, this is where Chiara's book is just so helpful, and was helpful to me in the same way that The Fabric of Reality was in terms of quantum physics. The science of Can and Can't just lays it all out for you. It tells you about information theory and quantum information theory, thermodynamics and epistemology in terms of the constructor theoretic view of what knowledge happens to be, and the significance, of course, of counterfactuals as part of physics. It's a wonderfully clear exposition of the theory as it stands right now, and I cannot recommend the book enough to anyone interested in the latest, deepest physics we know and how it connects to some areas of philosophy. So we explore the book today and lots more as well in this conversation. I even managed to press Chiara on that great issue of our time, the supposed looming superintelligence explosion, or the AI apocalypse. It was such a privilege to speak to Chiara, and although ToKCast is not about to pivot into being an interview show by any means, I will be speaking, I hope, to some more physicists over the coming months on ToKCast and AirChat as well, as we continue to explore the fabric of reality, both the book and literally the fabric of reality through the content I create and publish through various channels here. Without further ado, though, enjoy this conversation with Chiara Marletto. Hello, Chiara, and thanks so much for joining me for the 200th episode of ToKCast. My second only guest ever, actually. So it seems like on average, I get one guest every 100 episodes or so. So welcome.
Thank you.
Let's dive straight in. There's so many facets to your work, and I want to get to the substance of exactly what it is that you work on. But I thought first, it'd be interesting to know about what's brought you here, because you're in a particularly deep area of physics, and I've known a lot of people who have gone into physics, and your area is the deepest. Many people go into physics because they're drawn to astrophysics. They love the pretty images of space, or geophysics. There's money to be made by digging stuff out of the ground, and of course, these days there's very fashionable areas of physics like quantum computation. And, you know, if that pays off, that's going to be big, that's going to revolutionize things. But somehow you've managed to find yourself even deeper still than quantum computation. You found yourself at the very foundations of physics, and in fact, you're still digging. It's amazing. So can you take me back to Chiara, perhaps at school, perhaps any influences from your family that might have been instrumental there? You read between the lines in The Science of Can and Can't, and it seems like your father had a deep influence on you, and your journey from there as a child growing up in Italy through to undergraduate and finally to where you are now, perhaps the leading researcher with just a few others, a handful of others, on what purports to be a candidate for our deepest new theory of physical reality.
Yeah, actually thinking with hindsight is always interesting, because you create a narrative, right, for what you did, and I'm sure that there were a number of events during this story that caused me to do various things. But I think the way I think about it now is more or less like this, that initially I think I really enjoyed the idea of understanding the world in various ways. And I think this was clear to me already early on. I think when my fathers particularly, but both my parents, I think they liked to tell me lots of stories. And these stories really fascinated me as a child. So I loved storytelling. I loved the idea of creating some kind of, what I would call now an explanation about things. A good story is actually a good explanation where you put together the characters in a nice way, and then out comes a great plot. And then this love for storytelling kind of gradually turned into love for explanations, for having some kind of deeper understanding of things. And then in secondary school, I think I really liked philosophy, so I was taken by these early philosophers, the Greeks and so on, and it sounded very interesting that they were trying to understand these concepts like infinity and space and time and the universe, etc. And then only later I actually realized that I was looking in the wrong place, in the sense that, philosophy is very interesting, but the thing that really goes at the heart of things is physics. And so that's how, towards the end of secondary school, I matured this interest for science and physics specifically. And I thought that I would want to dig deeper and see whether, it was really the thing that I was hoping it would be, that it really could tell me something more about, the way that reality works. And then, this turned into a love for physics, this interest. And I think the most interesting thing that I still find interesting now is this fact that you can come up with explanations for what happens around you, and these explanations are unifying and they're universal if they're good, and they sort of really take you much deeper than what you can sense or perceive directly with your senses. And they tell a very interesting, compelling story about the universe. And I think the more compelling the story is, the better the explanation is, etc. And anyway, I think it was towards the end of my master's in Torino that I realized this fact that somehow this part of physics that was very interesting to me, for quantum physics, was also extremely mysterious. The way it was presented by teachers, right, and lecturers was very confusing, in fact, and at least to me. And so this brought me into thinking that maybe I would want to understand the foundations of this field. And so somehow asking here and there, it turned out that quantum information was the field where one could find perhaps a better understanding of quantum physics itself. And that's how I ended up doing a PhD in Oxford. So that's where I met David Deutsch and then Arthur Eckert and various other people that I started working with here. And that's how I ended up being a researcher, actually, in this field. And I think it's always been this interest for trying to find deeper explanations. I think that's the thing that really attracted me to physics and made physics so, somehow, I singled it out of various other disciplines that were also fascinating to me as the tool to understand reality. And that is really mind-blowing. It's something that perhaps you don't realize at first in school, as you've already pointed out many times, I guess, yourself. Often, teachers, maybe because they're constrained by various things, syllabus and various other things, they may not have the time to explain that physics is about this fascinating activity. But I think this should be said much more often to students, because it would cast a completely different light on physics itself, that usually is perceived maybe as a bit of a sterile, sort of a bit of a hard subject that doesn't, it's a bit sort of dry subject that doesn't really give you a lot of satisfaction maybe as you approach it at first. But actually this couldn't be further away from truth, really. Is really is really a very deep enterprise, and I guess that's why I'm sort of in this, and so far it's proven really exciting. So I'm happy about the choices.
I've seen you up on stage defending the Everettian quantum theory interpretation, the many worlds, the multiverse. I'm just wondering now, it strikes me, were you already on board? Had you already been persuaded that this was the explanation of quantum theory? Or did you have to wait until you met Arthur and David and you were in the Oxford community before you understood that? Or did you already go to Oxford understanding the Everettian interpretation?
So I was lucky that so initially I think the way I was presenting quantum physics in undergraduate, in my undergraduate degree was simply the usual way that is very baffling and confusing, which uses this idea of collapse, really, of the wave function, right? And I guess this takes you as far as, passing exams and doing calculations. But I think somehow if you start questioning, what is the meaning of all this, you start realizing that maybe this is not the right way of looking at things. So I was lucky that one of my lecturers, which was then the person that I did my thesis with, is this theoretician called Mario Rossetti. He had an interest in quantum information, and because of that, he had already been primed into thinking that that actually it's better to look at quantum theory in this reversible unitary way, which is at the heart of the Everettian interpretation. So even though maybe Mario wasn't, I would say, he may have been gently skeptical about the Everettian interpretation itself, he was very much in favor of this understanding of a measurement as a phenomenon that you can describe within quantum physics. So you can describe the observer within quantum physics and so on. And once you start looking at quantum theory this way, you see first of all that measurements make much more sense because they are described just like any other interaction that you describe within the theory. Observers as well, right? So they're just physical subsystems, and they can be as small or as large as you like. It doesn't matter. They all fit into the description. And I think that was something that I already had in my head when I sort of arrived in Oxford. And then in Oxford, I think the way in which quantum information works and how you think about things is deeply rooted into this idea of many worlds, and so in that sense it was then a kind of perfecting this understanding, and definitely I understood much more during the PhD when I thought more careful about some of these aspects with David and Arthur and Vlatko Vedral and so on, and other people here that sort of developed aspects of this theory in different directions. But I think I had this initial dissatisfaction with the collapse way of thinking about things, and somehow I was, once you enter quantum information theory, the way I did with my lecturer at the time, my thesis advisor, that sort of, I somewhat fell in love with the way of thinking about measurement and observers in a kind of unified way. And I thought that because it's consistent and it doesn't create problems, I thought, why complicate your life with collapses and other things that create other issues? Let's just go with what the theory says and see what the consequences are. And even if they are perplexing from a philosophical point of view, in fact, that's all the better, right? There's more to think about, and it means the theory is doing what it's supposed to do, which is to surprise you and give you a deeper understanding of things. So that's how I ended up here, I guess.
No special physics, no magic for the observer, no special way of needing to account for these things. Just have this unitary, universal theory that applies to everything, everywhere, all the time. Yes. So when we dig ever deeper, we find that things tend to unify. And, of course, this is shown by the unification between quantum theory and computation. You end up with quantum computation. And you're going deeper than that. There is this sense in which while the quantum computer, in principle, when we have a universal one day, will be able to compute anything that can be computed, it cannot itself transform matter. But this is where, and eventually we'll get there to talk about this in perhaps more detail. The universal constructor, however, would have this property. We don't know how to make one or anything like that yet. It's worth stressing, though, that constructor theory, that very term, can sometimes make people think it's only about this universal constructor, or it's only about looking for this universal constructor. But actually, it's a theory about counterfactuals, which you lay out so brilliantly in your book. Things that might have been but are not, or things that could be and might be brought about if only we make some effort, things like that. So it could be the counterfactual other universe that physically exists out there in some higher order space, or it could even be a universe with different physical laws. Constructor theory could, in principle, be able to deal with these different kinds of problems. Perhaps you could sketch the link for me between the universal constructor, or constructors in general, and counterfactuals. Perhaps begin by telling the audience, my audience typically very general, of what even a counterfactual is.
Yeah, so that is a term that I'm using, that we use together with David to indicate a particular set of properties that are relevant in physics, and they have to do with what is permitted, possible or impossible, and so it's as, you know, in kind of contrast with what usually dynamical laws are about once you specify an initial condition, because once you do that, you are telling a story about what happens, will happen, or has happened, depending on where you're looking at, in the universe or in space and time, if you like to have a kind of relativistic viewpoint. And it doesn't, because you single out a specific trajectory, you are avoiding mentioning other possibilities. And also because you're singling out a specific dynamical law, you're avoiding mentioning that there could be other laws that might well apply to describing and explaining what the phenomena at hand are. But you're not considering that in standard dynamics, because you have a particular dynamical law and then you see what the predictions are given some boundary or initial conditions. Whereas counterfactuals, counterfactual principles, for example, are laws that refer to this set of allowed or disallowed transformations. And in doing so, they also implicitly they rule in or out a certain set of dynamics and a certain set of initial conditions, but they have a sort of, they exist at a higher level compared to these dynamical laws, because they can constrain them. And so you can think of these principles about counterfactuals as guidelines for guessing dynamics and boundary conditions, and so theories of initial conditions, etc. And so you can see how they capture an additional aspect that is relevant to physics. And so in my book, and generally speaking in my work, I've been trying to find problems where this viewpoint is more fruitful and allows you, a set of methodology. It allows you to have a set of methodology at hand that otherwise you wouldn't be able to use, and so it's more effective at solving problems in those specific cases. Now, the connection between a counterfactual and constructors and universal constructors is more or less like this. So if you think of the universal constructor, the way that Von defined it implicitly is as a machine that can be programmed to perform any physical transformations that's allowed by the laws of physics. I guess this is maybe a slightly more constructor theoretic version of whatever von Neumann said in his writings, but I think that's the gist of what he had in mind, I think. And so this machine has a repertoire, right? So it has a sort of set of transformations that it can perform when given the right program. And there are a set of transformations that it cannot perform no matter what kind of program you provide in input. And if you think about what this repertoire looks like, it is a way of, it's really a set of counterfactuals. It's a set of rules that that somehow tell you what transformations are allowed and disallowed in the physical world. So there's a sense in which if a universal constructor is possible in a given universe, studying the set of transformations that it can or cannot perform is equivalent to studying the whole of physics, in the sense that the laws of physics put constraints on this repertoire of the universal constructor, and understanding why a universal constructor cannot perform some transformations, like, for example, creating energy out of no energy or something of this sort, is in fact understanding why there has to be a certain principle of physics that says that these transformations are disallowed or allowed. And so this is the connection. So the idea is that as you are building this theory of the universal constructor, which you can think constructor theory is an instance of, at the same time you go uncovering a number of principles that tell you how physical reality works. And some of these principles, we may already have some such, we have some of them already in a sense, maybe not formulated in a fully constructor theoretic way, but for example, thermodynamics is an area where principles of this kind, like the second law of thermodynamics or conservation of energy that I mentioned, already tell you a little bit of what are the constraints that the universal constructor has to deal with when, thinking of which transformations it can perform and it cannot perform. But then there are extra principles that have to do, for example, with information theory and other aspects of physics that we haven't really tackled properly yet. And the hope is that this approach with counterfactuals that constructor theory has allows us to formulate these principles, and then thereby adding supplementary laws to the laws that we know at the moment, and then allowing us to guess better explanations for physics. This idea that studying the repertoire of a programmable machine like the universal constructor allows you to understand physics and discover laws of physics is an idea that is deeply seated within the quantum theory of information. And I think this is a theme that is very dear to David Deutsch, because I think the way in which the way in which quantum information theory was initially discovered, also by other pioneers, was really that these people were trying to understand how quantum physics works, and they realized that quantum computers, and specifically the universal quantum computer, being using quantum theory's most fundamental properties, where these quantum computers were actually a good object to study to understand quantum theory itself. And now we are just expanding this logic to a wider set of machines that are more general than computers, and these are constructors, and hopefully to the universal constructor, which is the most general programmable machine that one can think of. And note that maybe the universal constructor is not possible, so we don't know if that's possible or not under the laws of physics that we have, but that itself is a way to understand how the laws of physics work and how reality works. So in that sense, it's part of this program to find out whether the universal constructor is allowed or not.
So even a failure would be a success in a sense, even if you were to find that you can't construct this thing called the universal constructor. That tells you something very deep about the laws of physics and the universe. Well, let's get to information then. What is information? I mean, we hear about it talked in terms of computer science. We also have the version of information that falls under the thermodynamic kind of rules as well. So what is information in the classic sense, and how is it different to quantum information?
So I think this is a very nice example of a property that you can only talk about in terms of counterfactuals if you want to provide a sort of satisfactory physics definition for what is information. And I think the way you do that is to shift a little bit the focus. Instead of saying what information is as thinking of it as a sort of substance or something like that, you say what transformations must be allowed on a physical system for it to contain what we all agree can be called information. And if you look at that, it's quite elegant and simple. You can notice that there are a couple of properties that you want a physical system of that kind to have. So the first property is the fact that it has to have a set of states that you can interchange. So if you think of a bit, there are two states, and you want to be able to flip 0 into 1 and 1 into 0. So these are two counterfactual properties, the fact that you can perform these tasks of flipping 0 and 1 into one another. And then the other property that you want is that these values of the states in question can be copied if you have a replica of this system, just like you can do with a bit. You expect a good bit to be interchangeable with another bit, and also if you have two bits together, you want to be able to copy the value of one onto the other, ideally to arbitrarily high accuracy. And of course, with bits, we take this for granted, but if you think of what this means in terms of physics, this requires a number of symmetries to be present in the dynamical laws that rule your physical systems. And not all physical systems have these properties, and not all dynamical laws allow for these properties. And so classical information really requires this idea of permutability of states, the fact that you can flip states into one another, and copyability. And then the way in which this classical information is different from quantum information is that quantum systems have extra properties. So not only can they embody information in this way, so they have sets of states that can be flipped into each other and copied in this way, but they have extra properties that some transformations are also impossible in this set of states. And the classic property in the case of quantum systems is the fact that if you take two different ways of embodying a bit that a single quantum system has, with different physical properties, for example, the orientation of a spin along a given axis, and then the orientation of the spin along a different axis. If you want to then use all of these states together to, as an information carrier, you will find out that you cannot. And the reason is that you cannot copy all of them simultaneously with the same device. So the copyability property fails at a certain level, in the sense that not all states of a quantum systems are copyable in the same way that 0 and 1 are copyable in a classical bit. And paradoxically, this fact that you have somehow more constraints, you have fewer possibilities available, so you have an extra constraint that says that some things are impossible, suddenly gives you extra computing power if you consider more quantum bits together. And that's one of the aspects that allows you to have, for example, things like entanglement and so on. But the key difference is really in this copyability property that has extra property. You have an extra constraint on copyability for quantum systems, which you don't have for classical bits and classical systems. It's
fascinating, isn't it? It's almost like a life lesson. There's more constraints, but it actually increases the power in some way of this system.
Yes, it's quite nice thought that sometimes constraints are good and they can open up possibilities. Yeah.
Yes, and we should say to people that anyone who wants to learn more about information and quantum information, I've never seen a more clarifying way of explaining this than chapters 3 and 4 of The Science of Counting Cartons. So, holidays are coming up, Christmas is coming up, so if anyone's got someone in their family or in their life who's interested in anything from the basics of science through to cutting edge physics and information theory, then this is the book for you, and it gives you a rundown of everything from quantum theory through to thermodynamics and even epistemology, and we're going to get there as well. But we've just talked about information, and there is this article that's out there, published 2014, New Scientist, that you co-wrote with David Deutsch. And I can guarantee that you guys did not write the title to the article, because the article is titled Reconstructing Physics, the Universe's Information, which is John Wheeler's position, the it from bit thing. And David Deutsch, of course, wrote famously it from qubit, where he counted all of that. So is it true, Chiara, as one of the world experts on quantum information theory, is the universe at bottom information?
No, and I think that the title was, happened as a sort of glitch in the in the process of publication. But yeah, I think that's good because we can then talk about the reason why that's not true. And the reason is that first, information is this entity that you cannot use. So it's something that is you can't use it as primitive. It's a thing that rests, as I said, on a number of properties that systems may or may not have. And in fact, there are systems in the universe that don't necessarily work as information media, so they don't have these two counterfactual properties that I mentioned earlier. So that already in itself says that the universe can't be information, just information, because there are other things that may not have those properties. And they're still physical systems, and we still, study them. And one example is exactly what I was going to say, what I was saying earlier, that you have these quantum states of a quantum system that they're perfectly allowed states, but if you try to put them together to embody a bit, you can't do that because they're not copyable. So that's an example of a system that you can't use to embody information in the way that one expects a bit should do. And then the other reason is that the way we think about information is really as a thing that is explained in terms of other things. So it's when you say that certain tasks are allowed, permitted to permit information to be embodied in a physical system, you are referring to some more elementary properties that these systems must have in order to information to be instantiated in them. And so these properties are the most fundamental things, and maybe even they could be decomposed into more primitive things. So the title is also problematic because it somehow suggests that there is this idea of a finite, a sort of ultimate primitive entity in an explanation that you can come up with in physics. And I think that's not the case. And usually in physics, when you find something that you think, oh no, now we understood everything and everything is done and dusted, there's always something that is a bit problematic. And then if you start digging a bit more in that direction, you find that there's a hole, and then this hole leads to a future theory. And so it's a bit, I think the title is also in a way too pessimistic, that it says that everything can be explained in terms of one thing. These things usually can be explained themselves in terms of other things, and that's part of the game of physics. That's why it's exciting. I would say constructor theory definitely is not about explaining that that's the case. In fact, it's trying to counter this position and providing more fundamental explanatory elements in terms of which you can explain information and other things. And they are based on these counterfactuals, as I was saying earlier.
But there are many true believers in the simulation hypothesis. Do you have any remarks on that? This idea that we are in fact inside a simulation. You haven't seen any fingerprints of the great programmer out there in your work?
Yeah, that's an interesting hypothesis in the sense that it's not. So sometimes in physics we have to rule out things as not necessarily just because we can't, we observe something that refutes them, but also because they are not good explanations. It's simply, it's a bit like when you discuss the existence of God. You can't disprove the existence of God by observing things, but you can say that, if you're a physicist and you're thinking about the world and trying to understand it, saying that certain things originated with it is not a good explanation, so we have to find something else. And likewise in this case, this theory is not explanatory because the programmer is not explained. So we have to, at least that's the way I think of physics, that physics exactly tries to take these things that are unexplained and build, decompose them into things that can be explained. And that's actually what, going back to the initial question, that's what got me into physics in the first place. And that's why I find it fascinating.
And I think David has remarked once before that if we were in a simulation, running on what computer, where, under what theory of computation. So
yeah, then you would have to explain all of that. And then that would itself somehow be a different theory from the theory that we are in a simulation.
Now, The Science of Can and Can't, your book, it contains not only this material, as I said, about information theory and quantum information theory, but there's a substantive section there on thermodynamics, and we've already touched a little on thermodynamics. Thermodynamics doesn't seem to sit, if you study a physics degree or if you do physics in high school, you might very well encounter some relativity, you might encounter some quantum theory. Certainly by the time you get to undergraduate, you're going to realise that these are the two theories that do encapsulate our best explanations of the world. But the laws of thermodynamics don't sit neatly in either of those, and they're a set of principles. Why are they different, and what is in particular different about the second law? It's always held up as having some almost religious significance in many areas of science.
Yeah, the second law is a very interesting beast because, first of all, there are many versions of it. And so when people say the second law, they often mean different things. Even specialists, they have, there's a way to think about it in the statistical mechanics sense. So Boltzmann's, way of imagining this law as emerging out of some procedure that allows you to say, well, we have a certain set of dynamical trajectories, and if we take some common sense assumptions about them, we end up noticing that the most likely point of equilibrium of a given system, when let it, to itself, has a certain property that we can summarize in terms of its entropy being sort of maximized. And then you have a different way of talking about the second law, which is the way in which Kelvin, Clausius, and the founding fathers of the phenomenological thermodynamics were thinking about it, which is in terms of this idea that you cannot convert heat into work without any other side effects. And so, that explains why you cannot use heat to power a boat and so on. And many others, actually. There are some nuanced, different versions of these various principles that I mentioned now. But the problem with all of them is that somehow they, just like with the whole thermodynamics, to go back to your question, thermodynamics is often thought of as being a collection of recipes that allow you to make some predictions. They're very useful to, to figure out how a heat engine, works and what's the efficiency and so on. But they are not that fundamental. So somehow they're always thought of as applying at this higher, larger scale, macroscopic systems. And if you go, however, down to the microscopic dynamics, that's the fundamental thing. So dynamics really tells you the whole story. And then because you can't maybe compute, sometimes the dynamics is intractable, you cannot solve the equations, it's useful to have some thermodynamics helping you out there. But it doesn't really tell you much nothing fundamental about the universe. That's, I think, a very widespread view in physics, and certainly what you get maybe the first time you encounter thermodynamics in courses. However, there's something to be said about that in the sense that you can question that statement, and in fact imagine that perhaps the reason why the laws of thermodynamics appear to be just applicable to this macroscopic scale is that we haven't really expressed them properly. So there could be a way of formulating them in such a way that they are still compatible with the fundamental dynamics that we have for microscopic particles, but at the same time these laws add to those dynamical laws, simply because the thermodynamics is formulated at this higher level of abstraction where you're not picking a particular formalism, so you're not expressing them in the Newtonian or Hamiltonian formalism, or in the applying Schrödinger equation to a particular case. They are formulated at the level of abstraction of principles, and so they have this power of allowing us to single out specific laws and say that they are allowed and others are not. And so if we had an exact, more precise version of the second law, this would do us a great service, because we could then use it in order to guess maybe future theories of physics, etc. And in a sense, I think thermodynamics has been used in this way in the past, secretly in a way, but physicists have been using it in this way too, except that, as I said, it's still difficult to do that because the principles are at some scale just break down, so you don't know what they tell you about a specific system. So that's one aspect that makes thermodynamics at the same time interesting but also frustrating, because it has this feature of being incomplete in my view. And then there's this other aspect which is one of the most interesting ones, which is the fact that the second law particularly is a law that says that there must be some kind of irreversibility occurring at a certain scale or in some sense. Now, what the irreversibility is, whether it's the fact that once you convert work into heat, you cannot go back without side effects, or the fact that once you increase entropy and then the system is isolated, it just stays there. So there are different ways in which people think about irreversibility, but there is this idea. And unfortunately, irreversibility appears to be just in conflict with the fact that the dynamical laws that rule the microscopic dynamics are time reverse symmetric, so they don't display irreversibility. So there is this conflict, and that's also why people tend to think that thermodynamics can only hold in an approximate way, because they say, well, if the dynamical laws are true, then it must be that to get some irreversibility out of something that's reversible, we've got to do some approximations. And that's true in Boltzmann's case. It's true partly in the thermodynamic, phenomenological thermodynamics case of Clausius and Kelvin, etc. And then again, here I want to say maybe that's not true. Maybe the reason why we are finding this hard to reconcile these two things, irreversibility and reversibility, is that we are not expressing the irreversibility at the right level, so we're not using the right tools. And this is where constructor theory comes in, because I think that there's a way of talking about irreversibility in terms of the fact that a task is possible in one direction but not in the reverse, which is still compatible with the fact that dynamical laws are reversible, simply because a task being performed doesn't correspond to the fact that the dynamical trajectory is allowed. So there are two different concepts. And so the fact that you say that the task is possible in the forward direction but not in the reverse direction doesn't necessarily contradict the fact that the trajectories of particles that compose the substrates of these tasks are in fact reversible in the way that we expect them to be. And so that's what I've kind of been discussing in the book, and I've been working on in my work with some collaborators here. And that's very exciting, because it kind of gives you a way out of this apparent dichotomy between reversibility and irreversibility that you're stuck with if you stay within the traditional conception of physics.
So this way out, would that involve showing that a constructor cannot be built, which would now enable you to reverse certain processes?
Yes, and I think this idea was already there in the relatively early days of thermodynamics. For example, Planck has a lot of writings about this, and the key experiment where, a Joule experiment where you have a sort of isolated, adiabatic isolated enclosure with some water inside, and you have a stirrer that can sort of be actioned by mechanical means to increase its temperature. That's one task. So increase the temperature of this jar of water by mechanical means only. It's an example of a statement of the kind, there is a constructor that can perform the task in this direction, so of increasing the temperature. But then if you try to look at whether there could be a constructor that can perform the reverse task, meaning cool down the bucket or the jar of water by the same means, so just by using mechanical means, by stirring, you will see that there's no such constructor. And there's not because you haven't thought hard enough, it's simply because that's one instance of the second law. And Planck already had this, I would say, constructor theoretic intuition. In fact, I was very much inspired by his works, in the sense that he is already talking about the fact that in one direction you can have a cycle that can perform a transformation, and in the opposite direction there isn't such a cycle. And the cycle is really a constructor, so it's an object that can perform a transformation, then be reset to its original state without undoing the transformation itself. And now this is okay in standard thermodynamics, we know this, but if you now try to elevate this to the rank of a principle, and try to imagine exactly a statement of the second law that says the constructor is allowed in one direction but not in the other of a given transformation, and you see you want to see whether this statement is compatible with the fact that the dynamics that rules the elementary components of these entities is a reversible dynamics, you will see that actually the two statements are compatible. And it's simply because the fact that you have a task that's performable by a constructor in one direction but not in the reverse isn't in contradiction with the fact that the dynamics that you're running is reversible. Because if you run the dynamics in reverse, you're not performing the task in reverse. I think that's a very subtle idea, and my collaborator, I think Maria Violaris, was the person who actually demonstrated this within a sort of quantum model, even with an actual system, showing that this is the case, that reversible laws of quantum theory are compatible with this statement, and that's fun, that's interesting, and it's a hope to have actually a formulation of the second law which is exact. So it's to do really with how hard the task is in one direction as opposed to the opposite direction, and you can be even quantitative about this, just in a slightly different way from the usual way that you do in thermodynamics with entropies.
So if you were to stir your sugar in your tea, on average, the kinetic energy of the particles inside of your tea is going to increase, simply because the one measure of temperature is that if the average kinetic energy of the particles is a measure of the temperature. Now, there's no such stirring that could go on which would slow down the particles. In fact, if you wanted to slow down the particles, you'd have to have information about them and then to break them in some way. And that seems to be, at the very least, an intractable task to do.
Yes, so you could do it with other means, right? So you could cool down the bucket of the jar of water or the tea, but you would have to use a heat sink, which is not just a mechanical source of work. So you would have to sort of allow for some kind of dissipation, if you like, or you would have to sort of involve in the constructor an additional element that wasn't there in one direction. So that's the idea. So the same kind of constructor that works in one direction doesn't work in the reverse direction. And this is true for many tasks. So in fact, this view of thinking of the second law allows you to generalize it to other realms of physics, where you may not have something like a thermal equilibrium or temperature and things like that, but you still have this irreversibility present because a certain task is harder one way than the opposite way, where harder means what I just said, that a given constructor in one direction doesn't work for the backward direction.
Now, you're working on some of what I would say the most interesting and deep problems in the entirety of science. And I know you don't have a huge social media presence, so you may miss the fact that the topic du jour at the moment is the oncoming apocalypse from the AI and AGI people who think that superintelligence is about to take over the world. And they might very well be screaming at you, Chiara Marletto, that you should be using your brain power to try and solve this, to try and stop the robots from taking over the world. Have you got a view on this at all? It is the topic du jour at the moment with GPT-4. People are very, very excited that these things are about to become self-aware and self-improving and escape from the box. What do you think about how close we are, if that's the right word, to AGI, and whether or not AI is going to escape from our control?
Well, okay, on how close we are, I'm not an expert. I think it seems to me we are very far, and the problem is that actually we don't even know where we are. That's the problem, because it seems to me that we don't have an understanding of what the target is. So the problem with this study in artificial intelligence is that for sure there are some technological developments that are stunning and interesting, that no one denies that, but somehow they're not doing what we would be hoping they should be doing, in the sense that we don't have, I think, a theory, a good understanding, a good scientific theory of what the capacity, the capacity of the brain is, in the sense that we don't have a way to define properties that, like creativity or originality or consciousness. We can call them in many, many different ways. Intelligence, I don't mind which terminology you use, but we all know roughly what we mean, but we don't have a theory of what that is, like a scientific theory that tells us that's what we want. So therefore, when we have a particular way of dealing with certain optimization problems within a programmable machine, then we say, oh great, we are sort of doing what you were emulating human thinking. That's, to me, is very hard to believe, because we don't know what human thinking really does. Of course, we know at the microscopic level what happens in the brain. There are atoms and they obey quantum theory. Then at the high level, there are neurons, and we have an understanding at the medical level of various things to do with currents and synapses and various other things. But then there's the gap between that understanding, which is good, and the higher level description of what's going on in the mind when we come up with an idea. And so in that sense, I think we can't say that we're making that much progress if we haven't, first we should develop this theory, and then we can then say, oh, okay, look, we managed now to do this and that and that. So that's my view on that topic. The other aspect is, should we worry about it? Well, yeah, I mean, I think you should be, that's a question that you can ask about lots of pieces of technology. And, well, more than worrying is more like we should think about having a good, a good basis in the society for how to use these things. And these are things that I guess scientists can't help much with, not at least in their profession. So scientists do think about the stuff and they produce things, and then these things get used, and they can be used in a good way or in a bad way. And it seems to me this is the problem that happens with any technological development that is disruptive. Just think about when cars came about, right? So I'm sure that people were worried about people being run over in the streets and so on, and then there was an issue of how do we regulate these things, etc. And then some rules were put on, and then some of them were ridiculous, but others were not. And then the rules that were ridiculous were removed, and gradually we've co-evolved, etc. So I think these are problems that exist not specifically in relation to this technology. I don't see this as a particularly, as a singularity. I think it's just another kind of technology that we are developing, and we have to, of course, think about how to use it wisely. And finally, I want to say this thing, that there is this aspect that we can't even know. We don't even know how to instill in a human, how do we create, this is something that probably teachers are, very much interested in, and parents. How do we help a human being that's growing up, for example, to become passionate about knowledge, and become passionate about having new ideas, or never mind whether they're growing up, even adults. How do we make someone interested in things and creative? And I don't know, there are theories about education. Some of them are good, others not. But we don't have an understanding of how this process works. And so this is a very big problem. It's a big problem because we have lots more time on our hands because of technology, which is good, at least in part of the world. But then I'm not sure we're using the time properly. So it would be nice if instead of wasting the time, we could use it to do something creative.
It's a very important point. I mean,
yeah.
The discussion right now is all around AGI and trying to find avenues to AGI, concerns about AGI. But actually, we've got these things, GIs, these people, these children, and we don't even know yet how to maximize, as you say, their creativity within ourselves. So never mind the artificial version, the natural version has enough problems, I suppose. So that's one hobby horse. Another hobby horse that arises out of your book, which I'm absolutely fascinated by, which is the question of fine-tuning, the fine-tuning of the constants and the laws of nature. You seem to have been inspired, a little at least, by the Goldilocks Enigma, which is one of Paul Davies' many books that touches on this topic. And it was one that was specially focused on this issue. Often Davies writes these grand books that cover a whole lot of things, but this book is a great one because it focuses in on the question of fine-tuning. For listeners, the problem seems to be that the constants of nature or the parameters seem to be fine-tuned. And then, indeed, the laws themselves seem to be fine-tuned for life. Change this or that parameter and forget about life in the universe. You know, you won't perhaps even have a universe. It might be a matterless void, or it might just be one big, huge ball of hydrogen, something like that. If we start changing the laws of nature, we seem to radically transform what's possible out there. What does constructor theory add to this discussion, if anything, about the mystery that it seems to be fine-tuning? Because some people have denied it's ever been a problem. I remember the late Victor Stenger, one of his final books that he published before his death was The Fallacy of Fine-Tuning. And he was a particle physicist who denied there was even a problem here. Nothing to see here kind of thing. But many people since have written books to say, no, this is a real, genuine problem. Does constructor theory add a new window on the question of fine-tuning?
Yeah, this is an interesting direction, something that is one of those maybe unexpected things that maybe constructor theory could be could be of help with. So the first thing to notice is that the formulation of the fine-tuning problem is itself a bit problematic, in the sense that when you think of varying a law of physics, there are many different ways in which you can do that, and it's difficult to define a distance in the space of all theories from the theory that you have, because it depends what you are varying, but you may be varying some constants in the laws, or you may be varying the form. You can add terms and see what happens if the terms are growing in magnitude and so on. But it's really a very difficult job to guess in which direction to make a variation. And so it's difficult to be quantitative about what is a small and what is a big variation in a given a particular law. So that's already a problem. And the thing that constructor theory brings in here is that first of all, it gives you a way to see that if you formulate the laws in a different way, you will see that what counts as a small variation in this other way of formulating the laws may actually be a very big variation in the standard way of using dynamical laws. So in the case of constructor theory, imagine you have instead of your dynamical law that, Newton's laws or whatever, quantum theory's laws that are probably more closer to truth than Newton's. In that case, you just have this dynamics and you can vary it in the ways that I said, or other ways. And notice that if you do that, you end up with laws that don't even allow for things like chemical bonds to occur, and so therefore the very basic building blocks of reality are just falling apart, and so let alone life. But in constructor theory, you have a different way of formulating the laws, right? So you have this set of principles that basically have, if you imagine the set of all possible transformations, they divide it into two camps, one being the possible transformations and the other being the impossible transformations. Now, what is a small variation there? I don't know, but it could be that a small variation is a small modification of this boundary of what is possible, right? So you could slightly enlarge it or make it smaller, and so you have fewer tasks available, and which tasks do you choose in order to make this variation? So all of these questions are not answered, but they are there to illustrate that supposing that you take this view about how to make a small variation in the constructor theory way of formulating laws, and then you want to see what that looks like in the traditional conception of physics, you will see that the change, so what you're changing is a set of tasks being possible, but you're still requiring some tasks to be possible. And that doesn't correspond to the small change in the other camp, in the traditional conception of physics way of formulating things. So this is to illustrate that we don't know how to formulate the problem in the first place. So that's one first thing to say. The other thing to say is that if you look at the laws in constructor theory, and you consider the fact that if you want some tasks, this is a long argument to be made, but in short, if you want a task that requires objects of a certain complexity to be created out of elementary materials, you will always require a number of things to be allowed by the laws of physics for these tasks to be possible, for this complex object to be producible out of elementary building blocks. And these things include stable bonds. Not only that, they also include life, entities that can error correct to be around so that the task can be performed to better and better accuracy, etc. So a small variation in the constructor theory sense, so changing just a set of tasks slightly that are possible, doesn't necessarily mean that you end up with a huge variation in the possibility of things like life, but not only life, chemistry and other things. So it doesn't seem to, so this seems to indicate that if you take a naive way of changing the laws by a small variation in constructor theory, you don't incur in these bizarre, huge variations that lead to a problem as in the traditional conception of physics. Now, this is a speculation, so it's something that we haven't really worked on, but I think it's an interesting lesson somehow that constructor theory teaches us at this level, that something that looks like a huge problem in a given formulation may not exist in a different one. And watch this space in the sense that I don't know how this will end, but it's an interesting consideration.
Yeah, well, constructor theory opens up a new way of looking at traditional problems in new ways, which is always a promising avenue for our ability to make progress. One of the most exciting parts of the book, and which I say again, it's not just that the science of can and can't is a pure science book. It also is a book that I would say comfortably fits alongside The Beginning of Infinity, The Fabric of Reality. It's like a cousin to those books. And it's in the lineage of, Popper's great work, the Conjectures and Refutations, because you bring a new understanding, a constructor theoretic understanding of knowledge, and you have a parsimonious way of distinguishing knowledge from information. We've already talked about information as being this entity which has the property of being able to be flipped and copied, or in the case of quantum information theory, some of those copies are impossible. But what is knowledge, and how is knowledge to be distinguished from any other kind of prosaic form of information?
So this is connected to this problem we were talking about earlier. So we don't have a theory of creativity or how we create knowledge. Well, I don't think we have even a theory of knowledge. That's the problem. So we need in physics. So that's maybe the first starting point that we need to deal with. And in constructor theory, you can give some hints as to how you could do that, because you have this nice handle that on information that is using constructor theory allows you to describe information in terms of these physical systems that can contain it, and it's their counterfactual properties, so this copyability and permutability of states and so on. And then you can say, well, knowledge is actually a special kind of information, so of this thing that can be embodied in these physical systems with the properties that I just said, with extra counterfactual properties. And the extra counterfactual properties are the fact that this kind of information has the ability to to cause transformations on other physical systems, and to retain the property of causing it again. So this is, in a sense, an idea of resilient information. So it's information that tends to hang about and stay there and sort of not evaporate very quickly over relevant timescales of a given dynamical system, but it just stays there, and it's almost like an invariant property. And this entity, you can describe it in terms of this ability to stay instantiated in physical systems, which is a counterfactual ability or a counterfactual property of the particular kind of information we're talking about. And it's nice because it seems to me this decouples knowledge from subjects, knowing subjects, and so in a way this, of course, is rooted into these ideas of epistemological ideas of Karl Popper's and David's ideas as well, and nicely decouples therefore the idea of knowledge from subjectivity and things that are maybe one of the reasons why this idea of the problem of having a physical theory of knowledge isn't taken that seriously by physicists, because they're usually repelled by anything that sounds, even remotely subjective. Whereas with this way of thinking about it, you can actually bring it closer to physics. And it's very much in line also with ways of thinking about knowledge in biology, or in fact information that's relevant in biology, because of course parts of the genome are some collections of genes do instantiate knowledge in this way, because they have this property of imparting, giving instructions to the cell about what to do, as well as also they have the ability, if they are successful in a given environment, to perpetuate themselves through various, generations. And so in that sense, it's nicely friendly also towards biology, this idea of knowledge. And so we are hoping that this can be used to also further our understanding of things like the origin of life, the early life stages, where we still maybe don't have as deep an understanding of what happened as we do, say, in the case of evolution, where we already know, that Darwin's theory works. But somehow the early stages from the very beginning to when evolution can get started, there are some discussions about how this could have happened, and I think hopefully this kind of knowledge, this new notion of knowledge, can help in clarifying some of these aspects.
It's one of the most exciting areas of constructor theory, the linking of biology, epistemology and physics. One of the most powerful points that you make there very early on in the science of Can and Can't is how there are certain bacteria that essentially have gone unchanged for billions of years. So you can look out into the physical environment, see mountains, see rocks, and think, there are resilient things that have been there. Geological time is just so long. But in terms of what is truly resilient, it's those DNA strands in that primitive bacteria outlast all of them. I mean, we find archaea that perhaps stretch back that 3.5 billion years. No mountain range has lasted that long. No rock has lasted that long. And yet we have this deep physical problem. How is it that this thing has been so resilient for so long? Well, it's the knowledge, but what does that mean? How in fact, is it maintaining itself in that environment? It's a curious thing that for the overwhelming majority of the evolution of life on Earth, bacteria was doing nothing. DNA was actually doing nothing, sitting there rather inert, not evolving, not changing. But presumably there would have been environmental selection pressures, but nothing was happening.
Yeah. It's very interesting. I think these questions are interesting also, going back to this risk of technology and so on. These questions are relevant because if we could have an understanding of knowledge that is rooted within physics and also theoretical biology, we could then tackle this issue of how do we create knowledge, how is it that knowledge comes into the world in a more, I would say, scientific and way that would allow us to also make progress maybe in this other sector of sort of finding ways of creating AGIs and so on. So I'm hoping this will happen.
And just one final question before we finish up, not to do with constructor theory, but to do with, you've proposed with some colleagues an experiment for testing general relativity in the under the quantum regime. Can you speak a little bit about that? I think it's a rather unique approach to a possible experiment, and what are the holdups in actually doing this experiment?
Yeah, so this is work that I've been doing with Vlatko Vedrel, who is working here in Oxford. It's actually an example of an application of constructor theory's principles in an area where we don't have a settled dynamical law with which to make predictions. So as I think everyone knows now, the way in which we describe gravity is basically with Einstein's general relativity, and this theory is classical in the sense that it does not have, it doesn't permit quantum information, right? So it doesn't have quantum superpositions, it doesn't have any of the features of quantum theory. So gravity is a classical entity in this sense, so it doesn't allow for superpositions. Whereas masses and energies can exist in superpositions of different values, because that's what quantum theory says about particles with masses and also energies of these particles and so on. And because anything with energy or mass gravitates, there is a problem, because then what happens when you have like gravity interacting with something that is capable of being in a superposition, like quantum theory says? And this problem has been around for a while. It's already pointed out by many people in the 50s, even before. I think Feynman was the person who maybe phrased it more clearly, with this idea of just thinking what happens when you have a mass in a quantum superposition, what does the gravitational field do with it? And as a result of that, lots of theories have been proposed. So there are lots of dynamical models that have been proposed within the quantum gravity program. However, they haven't been tested. And also they have problems conceptually and also the mathematical level. So in a sense, we are not really sure if we wanted to make a prediction about what does the gravitational field do when interacting with a quantum system. We wouldn't know which model to choose, because we have no idea of which one is the most reliable one out of the ones we have, and some of them don't work also in some regimes, etc. So I think what we realized with Vlatko is that we could use, instead of, so forget dynamical laws for a second, and think instead of principles, right? So that's the beauty of principles. They don't use like second law of thermodynamics, like conservation of energy. They don't use necessarily dynamics to express themselves, but they are general rules that you can apply even when you don't know what the dynamics is. And so likewise, constructor theory's principles about the information theory have this feature. So you can apply some of the theories, some of the principles of constructor theory of information to this system where you have gravity interacting with a mass, because both of them can be seen as approximate information media. And just the quantum mass is also a quantum information medium, so it has these extra properties. And when you do that, you can prove a nice result, which is basically a generalization of what we already know from quantum information, but it allows you to talk about a system like gravity that may not obey quantum theory, so it may not fit into quantum information itself. And that's why we need the principles of constructor theory. And this result says something like this, that if you have a system, for example, like gravity, that is capable of interacting with two other quantum systems and create entanglement between these two systems, then itself, this system itself, must have some quantum features. So it's like a statement of, saying that you've got a channel, you have a system that has some channel capacity, and if you can use it as a channel to create entanglement between two systems that can get entangled, like quantum masses, then you're proving something about that channel and the fact that it has to be quantum itself. So you're not really measuring anything on that system, so that's why it's powerful, this idea, because you don't have to measure anything about gravity itself, which is difficult. That's what is very difficult to do, because you need very high energies to do anything with gravity, because it's a very weak type of interaction. But you can indirectly check whether it's quantum by seeing whether it can create this entanglement between masses.
So does that mean it would rule out the notion that gravity is classical?
Yes. So if you could do this experiment in a laboratory, you would rule out the possibility that, gravity is described by classical theory, like general relativity. So it would mean that general relativity has to be changed in one of the ways that we thought with quantum gravity, or maybe with a different way, depending on where you're going. But I think it has to be modified to accommodate quantum features. Something that has been doubted by many, I think, most famously, I think Penrose had this view that somehow gravity would cause quantum systems to collapse at a certain scale, and therefore would end up, he would bet on the classicality of gravity winning over the quantumness of quantum systems. Whereas if we could perform this experiment and see entanglement, this would be a completely mind-blowing thing, because it would really be the first confirmation that, the first refutation of Einstein's general relativity as a classical theory, and also a corroboration of these programs for quantum gravity, for quantizing gravity, that haven't so far had any experimental or observational support. And the cool thing about this is that you can do this in a laboratory, so you don't have to go at very high energies, like, use things like particle accelerators, or consider experiments that involve early universe type considerations and so on. You can do this at relatively low energies. So this means that the general relativistic effects are not there yet. So it's a very funny regime where you can, go and check whether gravity is quantum without gravity behaving, without the general relativistic features of gravity being relevant. And this is the thing that was found promising, not just by us, but also by other people from the community of quantum gravity. And it's nice that this was, if you like, the sort of a byproduct of thinking about stuff in this information theoretic way. So that's, in a way, one example of the power of principles. Why is it that they are so powerful? Because even if you're just a pragmatist and you don't care about whether what's fundamental or not, which sometimes is a position that some physicists have, they prove useful, whether or not you think they're fundamental, because when you don't know which dynamics you need to use, you can appeal to them. And if you think that they are good principles, like locality, or the principle of some principles that are at the basis of information theory that anyone would think are good principles, then you can rely on them to make some predictions. And one of them is this prediction here, and that's very exciting. So we're really hoping that someone will do this experiment, and it may happen. So it is, people are looking for support for that.
So what's the hold up then? Why hasn't the experiment been done? If the recipe is there, is it a technical matter? Is it a funding matter? Is there something else?
So it's a combination of things. I think the masses, so one can make a quick estimate of the amount of, what would give a measurable effect on the masses, so a measurable amount of entanglement. And the masses that you need to generate this effect are slightly over the current limitations for what we can superpose in a lab. So I think it's something like 10 to minus 12 kilograms, which is more or less the size of, if you want to have a sort of approximate way of thinking about it, it's like a cell has that weight, a human cell maybe. And we currently can superpose masses that are 4 orders of magnitude, 4 or 5 orders of magnitude lower than that. But the reason why this is promising is that we don't need to go all the way to this particular number that's called Planck's mass, which is 10 to minus 8 kilograms, which is a huge object by quantum standards. It would require a lot more effort, and it's the usual value that people in quantum gravity thought would be relevant for seeing quantum effects in gravity, whereas this idea shows you that you can, in fact, do this with lower masses that are much closer to the experimental abilities that we have at the moment. So what I think this will happen is just a question of the funding, because this requires obviously a relatively long term project, maybe it's 5-10 years, And there are some teams in the world that have the expertise for this. They just have to, get on with it and decide to do it. Also we have to choose the right technology. So it's a difficult experiment, but it's not an impossible experiment, which is what most people thought would be the case for testing quantum gravity. And that's why maybe part of the scientific community was a bit skeptical about this program of quantizing gravity, because it just produced so far things that seemed to have predictions that were very, very far away from any experimental capability. So in a sense, some people started saying, well, if we can't observe it, why even why would you bother quantizing it? Which is an argument that I don't really agree with, but it's nice to be able to actually give some experimental confirmation or support to these theories out there. Also because we don't know which theory is most of them have problems. So somehow I guess maybe having some experimental way of looking into things would help us maybe having more information about how to tweak these theories or change them altogether and think of a different approach. So I think it will happen, and it's much closer to realization than it was before, but it requires a number of things, and also an international collaboration probably, because it requires expertise to be collected from different teams around the world. This is happening, so I'm hoping in a few years' time we can discuss how it went.
Yes. Well, thank you so much for your time, Chiara. As I say again to people, they really should go out and get a hold of The Science of Can and Can't. It's out there on audiobook format. You can get it as a paperback. It'd be lovely as a hardback gift for Christmas for anyone out there. But where else can people find out information about your research and constructor theory in general?
So there is this constructortheory.org website that you can find on the internet. There are lots of number of didactic resources on constructor theory, some videos, some explanatory material as well for as an introduction. And then you can also find information on my own personal website, which is chiaramarletto.com.
Okay, thank you so much, Chiara, and I hope to speak to you again soon.
Yeah, thank you so much. Great. Thank you.
If you'd like to support my work here at all at ToKCast, please go to www.bretthall.org. Here's the webpage, and there are links there to my Patreon support pages or my PayPal account where you can make a one-off donation. Until next time, bye-bye.